Hi everybody. As I've mentioned in class this week and on Blackboard, I've replaced the original video number 5 in the series of videos I've made for ENS316 on using R package unmarked to conduct an occupancy analysis with this updated version, and thanks to Carmen, who has helped to refine the code that I'd come up with. This new code will allow you to produce occupancy and detection probability estimates for each of the habitat covariates, as well as just doing the significance test. I know some students hadn't had a chance to look at that video yet, and so I'll start again from scratch with a brief description of what occupancy analysis is doing. There are essentially two ways that we can count the abundance of a species in the world. One is we can actually count the numbers of individuals. So we might have a bunch of sites. Imagine that these are sample sites in the Conondale Range National Park where we did our camera trapping. But we might do a live trapping study where we have arrays of live traps and we capture and mark, and do a mark recapture study to estimate the number of bush rats living at each of these sites, and then we can extrapolate that across the whole area. Now when we're camera trapping, unless our animals have unique markings, and some animals do, quolls do, goannas do, feral cats usually do, we've got no way of knowing how many individuals we're seeing. All we can do is tell whether a species occurs at a site, and we can look at the number of detections at that site. So occupancy analysis allows us to actually use these detections at each site to come up with another form of abundance. And as you might guess from the name occupancy, it's not so much about how many animals occur, but at how many sites the animal can be found. And so with the bush rat, for example, forgetting all about the number of detections at each site, we can tell from our summaries that we've done of the data using CamTrapR already that we have bush rats at any number of sites. So I've just gone through and arbitrarily chosen 1, 2, 3, 4, 5, 6 out of 2, 4, 6, 8, 10, 12, 14. I'll go another one. So that's bush rats occur at 7 out of these 14 sites, or at half of the sites, which also equals 50%. Now it's all well and good to identify that bush rats were detected at 50% of the sites, but what that simple estimate, I'll hop over this side, we call this the naive, I think I've spelt that wrongly, occupancy. I should have looked that up before I did this. Go with me here. What this assumes is that we actually find the rats at every site that they're at. And what we know, anyone who's into fishing or bird watching or any kind of nature study knows that just because you don't find something at a site at a particular time doesn't mean that they're not there. And what occupancy analysis allows us to do is to calculate, sorry, I'll come back over this side, to calculate P, I'll put it in here, which is the detection probability. Which allows us then to work out at how many sites that species occurred, but we didn't find it, to come up with psi, or occupancy. A detection probability isn't the chance of seeing or the chance of finding an animal, although that's partly the explanation. What it is the chance of detecting an animal if they occur there. And, as I think we can all intuit, given that we have imperfect detection probability, occupancy is going to be higher than purely how many sites we found it at. Now, occupancy analysis, as we're about to perform, takes into account this imperfect detection by studying the daily pattern of detection and non-detection at every site. And importantly, it also allows us to not only calculate the occupancy, but also the confidence intervals. And they are so important when it comes to looking for statistically significant levels of occupancy. We might, over the medium term, be looking to monitor whether the occupation of these sites differs significantly. So in other words, is a species population increasing or decreasing? And it also allows us to compare between different habitats or different seasons or various other sorts of different treatments that might be applied to our sites. And what we're really interested in our work for assessment tasks 2 and 3 is how occupancy and detection probability might vary between two broad habitat types, euc habitat and vine forest habitat. Okay, so I'll jump back over to the computer and we'll run through this new script. Okay, so I've been messing around with the code here. So as always, I'm going to start off by getting rid of the global environment because I don't want any of the objects that I've created while I've been playing around and or using other pieces of script to jump up and accidentally be loaded and stuff us up. So I use this simple command. We're going to need these two packages installed if you haven't already got them installed on your machine. As always, you only need to install them once. You will want to update them as time goes on, but once you've initially installed them, all you need to do with each new session is run the library for each. And I'm just going to clear away the console as well, which I can do just with this brush down here. It always looks sort of unhighlighted, but it works. Or alternatively, you can go up to Edit, Edit and Clear Console. I'm going to set my working directory. So the working directory I have set, what's really critical to us here is to use the detection history that we created for whatever our species of interest is that we might be doing an occupancy analysis on. In my case, I'm interested in Rattus fuscipes, and I'm just performing this on a subset of all the sites. So I'm setting my working directory. I'm not going to run that line of code there. I've just got that in there. If you don't want to remove everything in an environment, sometimes you might want to only just remove one object. You can just use this line of code, rm, and then whatever the object is out of here that you want to get rid of. And you would do that if you've run some code and then realize there's an error with your input, or for example, dat, you might accidentally load in the wrong CSV file, and you might want to just get rid of that, but I don't. So this is my Rattus fuscipes detection history that I created in CamTrapR. Look at video 4 to see how I did that. And let's just have a quick look at it. So what we've got, I'm performing this example on just this set of camera trap data from Balumba Creek. So we've got cameras 1 through to 12. You can see here 2 camera stations where the camera didn't operate the whole time that we had them set, so that they get NAs. This camera, BC12, stopped operating at day 9, after day 9, so it gets NAs as well. This is all created automatically in that CamTrapR code. And then across the top we just have occasion number, so these are the 24-hour days. So these cameras were out for 14 days. So what I'm going to do now is to create, to modify that to get rid of this first column, because all that we want in there, let's just have a look at it, is the actual detection history. We don't actually want the station names. They're kind of irrelevant to this. What we're interested in is occupancy across all the sites, which are each represented by a row, but we don't need to know which site or not. You will have created summary tables and maps that illustrate this during your CamTrapR routines. Next, we need to turn this into an occupancy frame suitable for use with unmarked, which I've just done, and then we just look at a summary of that just to check that it looks okay, and it does, doesn't it? We've got 12 sites, and it's telling us we had 111 instances where there were no bush rats detected, 24 instances, the ones are where bush rats were detected, and 33 NAs. So that sort of looks okay to me. And there's a bit more information here, and summary information for your interest. What we want to do now is to add our covariates. So the covariates I'm going to add to this are the vegetation. So I need to load the camera trap station. So this is the station that we had loaded in CamTrapR. I'll just call that so you can see what it looks like. So here it is, it runs across multiple rows, but we've got, you know, that all familiar station, longitude and latitude, the start and end times, and dates, and the habitat. Now what you need to do if you're going to look at habitat differences is use this short habitat column. You can just create it yourself. If you haven't picked up the table from the class communications, and all I've done is anything with eucalypt in the name I've called euc, and anything with vine forest I've called vine forest. Have a look at this too though. We'll look at the last few rows to make sure you catch this. What has just happened there is that sorry, it's not going to be in this example, but in the complete data set, the Rocky Gorge, the YF sites are all eucalypt sites. So sclerophyll is similar to eucalypt. Now what I want to do is create a table, a data frame, I should say, in which I add take the short habitat column and add it to the detection history. Let's just have a look at that. So I've just pulled that column out, so it's just sitting by itself, and now I'm going to say I want to create a new unmarked frame, occupancy frame, just as before, but including site covariates, which are named after cov, which are these. Let's do a quick summary. So it should be the same. These initial parts should be the same as our first frame object, because we haven't changed any of that, but now we want to see these site level covariates. And it's telling me, remembering that I'm only using a subset of all the sites, that there are 5 sites that are eucalypt and 7 that are vine forest. And let's actually have a look at UFO1. So there we go. It's the same frame. I've gotten rid of the camera station numbers, but I've added these covariates of habitat. So let's run our first model. So we always start with the simplest model, and the simplest model in this case, we'll call it M1. You could call it anything that you want. Has detection probability and occupancy as being unvarying. That's what this symbology here means. That means that it doesn't vary with any covariate. It's just consistent. Oh, and I better though change that to 1 because I've got 1 there. Let's just quickly check. I don't need to update that anywhere else. Nope. So let's have a look. It would actually run off UFO, the original frame, because I've said I'm not interested in covariates. It will read UFO1, okay. I mean UFO, okay, without that covariate info. It's telling me it's discarded 2 sites, and that's these 2 that don't have any data at all, that are all NAs. And now we can run the model output. And there we see there's the estimate. These are estimates for occupancy and detection, but we have to back transform them to make them make sense, because these estimates, of course, have to sit between 0 and 1, because they're probabilities or proportions. So I'm going to do that here for psi. So this is our back transformed estimate of psi, or occupancy, which is 0.731. What that tells us is that Radhauskas occurs at nearly 3/4 of those sites, if we take into account that we didn't see it at all sites because of imperfect occupancy. In fact, if we go back and have a look at UFO1 again, let's just see how that compares. So we've got 1, 2, 3, 4, 5, 6, 7. So we have Radhauskas at 7 of 10 sites. So it's not too far off the mark. Our naive occupancy here would be 7 divided by 10, or 0.7. Our clever estimate of occupancy has it slightly higher at 0.731. Where was I up to? Let's have a look at the detection probability now. There we go. Our back transformed detection probability is 0.237. So what that means is that there's actually only, let's just say a 0.25, a quarter of a chance that we actually even pick up a bush rat when they're present at the site. And this has been estimated by unmarked by looking at these patterns of detections and non-detections at all of the sites where bush rats occurred. So you can see this one, for example, 14 days, we only got a bush rat on 1 night. And that's not because these animals are migrating through the bush all the time. Most animals have a fixed home range. It's just because, like fish, they're just not always on the bite. And then I'm just going to calculate some confidence intervals around occupancy. So there's our lower confidence interval, the 0.025 level confidence interval, 0.37, and our upper confidence interval, 0.92, and I'm going to do the same. So there's our intervals around each of the estimates that we just produced. I'm just going to turn off my email so it doesn't keep beeping at us. So this is our basic model. It doesn't really tell us anything at all about whether occupancy or detection probability are different in the different habitats. We're going to start playing with that now. And this is where this updated script diverges from what you already, if you've already checked in on it, learnt from the previous video. So model 2, it's an occupancy analysis again, but this time we're going to retain detection probability as unchanging, and we're going to model whether there's any effect of habitat on occupancy. So let's have a go with this. Again, those two sites have been discarded, you don't have to worry about that. And here's our model output. So remembering that detection probability, there was no we didn't model any change in detection across the habitats, so there's no significance to look for because we haven't tested for anything, but we did test for whether habitat had any bearing on occupancy, and our probability here is well above the 0.05 level, so obviously there's no significant effect of habitat on occupancy of bush rats. In other words, those camera trap sites in eucalypt forest enjoyed a statistically identical occupancy rate to those camera trap sites in vine forest. Pretty cool, huh? Now let's just produce some meaningful estimates around these. So we're using this, going to use the predict function, which returns the parameter estimates for these models. So I'm just going through here now. Don't worry too much if you don't understand exactly what's happening at each step. Naturally, if you run into problems yourself when you're running this, you'll need to try and figure it out. And you can do that through trial and error. What I've essentially just done is I've just called up the estimate for psi, or occupancy, and it's this line here, type equals state, is what tells it that it's psi. But if you follow this pattern and this general numbering naming system, you'll be right. And I've then told it here to add type to the end of the estimate, just so that we don't lose track of what estimate is what. So here we have in eucalypt forest, that's the estimated occupancy, 0.76. There's a standard error, and then we've got the lower and upper confidence intervals. In vine forest, the predicted occupancy is a little lower, but not any significantly different. You can see the confidence intervals almost entirely overlap here. And again, just harking back to our model output for model 2, no significance and miles away from indicating any significance. So where did I get up to there? Fits M2 psi, so I've got to go through and do the same thing for detection probability now. And again, we've asked it to add the type of estimate on the end so we don't lose track, and you can see these are exactly the same numbers, and that's because we stipulated in the model, I'll go up here, that we actually didn't want to model a different probability of detection in each habitat, and it's done exactly as we asked. So it's redundant, I suppose, to call up each of these. Alright, and now what I'm going to do is just run another line to create an object called fits model 2, which combines psi and p into one frame. Let's have a look at that, and there they are. So you could just copy and paste that into Excel or Word and create a little table for your results section, if indeed you decide model 2 is the one you want to use. Remembering with these models, what we're doing is we're actually at this point just looking to see what conceptual model our data best fits into. So we've just run one model where there's no variation across habitat. We've run a second model where it's only the occupancy which is varying across habitat, and you guessed it, we'll run a third model now where only detection probability varies across habitat and occupancy remains constant. So let's do that. Here's our model output. This is interesting. We actually do have a significant difference here. We have a probability of 0.007, so quite significant. Let's have a look at what our outputs look like now. So I'm just going to run through here. This is, I don't have to run the predictions again because I've already done it up above. Otherwise it's just a copy of what we've done up above, but with the names changed to reflect that it's model 3 and they're changed throughout. It's very important that you do this properly, because if you leave some M2s in there, you could really screw up your results. So I've just done the the occupancy, and as you see, it's the same in both habitats. And again, that's because that's what we asked the model to do with constant occupancy. Now it gets interesting. Let's have a look at this detection probability, remembering that our model output, I've got to backtrack. I've made a boo-boo there. I've looked at the wrong probability. I got excited. I saw all those zeros after the decimal place, but of course this is the one we need to look at. So sorry folks if you've scrambled off and got excited about your results in the meantime. This is suggesting there's no significant difference in detection probability. Let's just have a look at this next output. I'll just check that I'm in the right spot. And there we go. They're a little bit different, the numbers. So we've got ranging from around about 0.2 to 0.28, depending on whether we're looking at those camera trap sites in eucalypt versus vine forest. But the confidence intervals are overlapping, which, as we know, suggests that there's no significant difference and confirms this model output up here, this probability of a significant effect of habitat. Remember, I've said it already a couple of times, but remember that I'm just working on a subset of all of the data, so you shouldn't be running this script and expecting, pardon me, to be getting the exact same numbers. Not unless you're doing a test run on just the Balumba Creek camera trap outputs. Let's have a look. Fits M3P. I've told it that I wanted to add the type of estimate there, which puts us down to here. I'm going to combine those two sets of estimates. So we've got our two occupancy estimates and our two detection probability estimates. I just have a quick double check. It's always good, especially the first time you're running this, but I'd say probably any time you're running this sort of analysis, just double check that what you've got in here reflects what you've outputted here. Just as a little cross check that you haven't got, you could easily have a M2 in there rather than a M3. Right, so we've created these three models. None of them really suggest that there's an effect of vegetation on this small subset of the data on either occupancy or detection probability, but we still need to figure out which of these models our data fits to the best, and so which set of occupancy and detection probability estimates we're going to use in our reporting. And we do this using the AIC value, Keikie's information criterion it's called. It might sound complicated, but fear not, it's actually pretty simple. So what I've done is I've created a little frame combining the AIC values for all of these. Oops, wrong part. The AICs for all of these, and you're just using the inbuilt functions within the package, and then I've just called the object. And so here we have our three models and their AIC value. The way we use AIC model is value is that the model with the lowest AIC out of any set of models is the one that produces the best fit to the data, using the least amount of or losing the least amount of information. So the best model is always the simplest model that works, and that's essentially what this is doing. So what this suggests to us is that model 1 is actually the best model. Now, given that these are so close, there could be an argument mounted that they're all pretty much equally performing models, but we're going to keep it simple here and stick with just, a fairly simplistic view and use just the smallest AIC value. So that's model M1. So in order to get that information that we need for our report, let's just create a little table which compiles the outputs, and here we have them. We have the psi, the estimate, and the lower and upper confidence intervals, and P, detection probability value, and its upper and lower confidence intervals. Given that we found no significant difference in any of these parameters between habitats, it makes no sense whatsoever to present results with different estimates. So hence we're not going to, in this case, present the outputs for, let's say, model 3, which came in a close second. And we produced fits M3 up here. This is where we bound that data together. I'll just run it again just to remind you what it looks like. So there we have, it's the same kind of output as we have here. It's just a bit rawer in that I haven't gotten rid of these other columns. So there we have that. Now, as well as, let's just run this one again just so that you're not confused about what I'm doing here. I'll just turn that off again because I don't want it. This is the one we want, so we would present that as a table, but it may also be useful to present it as a plot, and you can do it using this bit of code. So here we have those estimates. So for detection probability it was 0.23, so there you are, just shy of there, and their standard errors, so not their confidence intervals, but oh no, these are their confidence intervals. I've had those mixed up. So there's P with the confidence interval of, yep, and there's our occupancy with a confidence interval down at 0.4 or so, all the way up. Yep, so that looks good. So there we have it. Using this updated bit of code, it's really just these bits in the middle here that are changed, but it just allows you to pull out those habitat-specific estimates if indeed you actually need to do it. And you'd only do that if A, you get significance from your model outputs, and also if those models prove to be at the bottom end of the AIC values in your suite of models. Just one final little bit of advice with AICs. It's generally considered that if an AIC value is within 2 of the lowest AIC or any other AIC, they're considered to be not statistically significantly different, and therefore either model could be equally as good a fit for your data. So as I said before, in this case, less than 2 between the best or lowest AIC value and the highest AIC value. So if you wanted to get fancy, you could start doing things like averaging model parameters, etc. But we're not going to go into that now. I'm perfectly happy for you just to take that lowest AIC value. So I hope that helps you to get a little bit more information out of your modelling and out of our camera trap data. And remember again, I've done this only on a subset, so you might actually get some significant differences along the way. I look forward to hearing from you and seeing your reports in a bit over a week. Scott out.